Hello, my name is Ábelová and I'm going to talk about predictive control in a power system. So, where are the problems when doing a control? We use models, but they are not accurate. We use them to predict future states, but in reality, we are not able to do it exactly. And second issue is that we would like to react faster than is the dynamic of the processes. So we have to include uncertainties in the control problem. However, that comes with increase in the computational complexity. And here I'm going to propose a general method that can deal with both of these issues, and it will be explained using real data applied on a real system from domain of energetics, especially microgrids. And this is how a microgrid might look like. It's a power network that consists of some kind of energy source, preferably from renewables. It has its own consumption, a storage unit, and might be connected to the utility grid. And then not limited to these, there might be heat pumps, diesel generators, or any other energy sources. And we want to optimize these power flows between individual assets. So we have to design model predictive control that makes decisions in real time. We have control over these two. We can set points how much battery should be charging or discharging, and how much power should be imported or exported to the utility grid. And these can be only estimated, like how much power will be produced or consumed within the microgrid system. However, the models can't be 100% accurate. There will be some deviation for sure. And to capture this uncertainty, we trained a neural network that outputs also a confidence interval within should fall, let's say, 90% of future outcomes. So in 9 from 10 cases, real production will really be within the bounds. And in the example, it can be seen around 8 o'clock, there is a higher uncertainty as bounds are wider, so probably some clouds are passing by. And to design a model predictive control able to handle uncertainties, we generate multiple scenario trajectories of possible power outcomes within given bounds, and then use a stochastic approach. And alongside the power production, we have to estimate power consumption, and we could predict any quantity that may have influence on total costs of the system, like carbon intensity of the utility grid, market prices of the electricity. Then the cost function of microgrid systems may contain some or all of these terms, and the aim is to reduce operational costs consisting of electricity costs, demand charges, our carbon footprint, but without overusing our assets like battery storage. And the revenue may come from selling generated energy and maximizing utilization of renewables. So this is how 20 scenarios may look like, and each scenario is associated with the costs we would like to minimize. So in the example with 20 scenarios, probability of each is 5%. So I assume probability of occurring each of them is the same, but they are already generated with the Gaussian distribution. Better to see here with the thousands of scenarios, but now it's not desirable to optimize towards the expected costs. The action would end up the same as with the nominal forecasts, but neither towards the worst case as in the robust control. The action might be too conservative. And what is needed is to introduce risk measures such as value at risk. Value at risk can be interpreted as the maximum cost that will not be exceeded with the probability 1 minus alpha. So with our actions, we can be 1 minus alpha% sure that the costs will not be worse than the value at risk. And this allows us to optimize towards the worst alpha quantile, since conditional value at risk is the expected value of the costs that fall beyond the value at risk. Here the picture compares expected results when low risk action was taken versus higher risk action. So in the latter, the expected costs is slightly better, but in a few cases the outcome will be much worse, and we want to avoid that. So it was said that we are not going to optimize the expected costs. Instead, we minimize the risk represented by the conditional value at risk. Unfortunately, there is a known linearized form that how to express the risk measure that could be included in the objective function. And we gain another benefit, and that is a tunability. With the alpha parameter, it's possible to set our risk aversion. Like with high 100% alpha, we are back to the minimizing expected costs, and with very low alpha, we have robust control towards the worst case. The model of the whole system and the models of individual assets in form of equality and inequalities are included in the constraints. And constraints, for example, in each time step, it must be ensured that the power production is in the balance with the power consumption. And there are other technical or business limitations. So at the beginning, I said there were two issues with the real-time control of the real systems. So far, we dealt with uncertainties, but still the problem with the solving speed remains and is much severer with the increasing number of scenarios, and they add another dimension to the MPC problem. And what quickly means, so what is fast enough in energetics domain? So the standard time unit is a 15-minute interval. That's also usual sampling of the horizon, but actions must be computed more frequently. Now I'm getting to the idea. If we know which scenarios belong to the worst alpha quantile, the expected value of these selected scenarios equal conditional value at risk. And we can identify them and compute corresponding alpha scenario. And then solve model predictive control problem, but just with this one scenario, and get the same results as optimizing towards the worst alpha quantile. So no need to solve each of tens or hundreds scenarios anymore. And since the complexity is not linear, that means 100 scenarios don't take 100 times longer than one, but much more. The complexity reduction is significant. So the procedure is as follows. In the first step, it is necessary to solve stochastic model predictive control problem with the multiple scenarios, but we can use a low fidelity model because it serves just for identification of the worst scenarios and computing a single one that's passed to the second step, where regular MPC problem is solved with the just single trajectory of all uncertainty parameters but using high fidelity model. And what I mean by low and high models, so low could be relaxed, simplified, linear model with a longer sampling interval to reduce the complexity as much as possible. Any simplification that could be afforded. And then in a second step, we use model that is actually deciding about the actions, might include binary or integer decision variables, be nonlinear. computation time of this approach, even when MPC must be solved twice, is much lower compared to conventional stochastic MPC that uses multiple scenarios with a complex model. And how much? That of course depends on the models. For example, with our case of a particular energy systems, we were able to reduce solving time up to 50 times. And these numbers were obtained in a setup with 50 scenarios, and that number was chosen according to technical limitation that solution should be found within 1 minute on a particular computing device. So with these numbers, I already got to the results of the real case application. And as I promised, the proposed methodology is deployed to operate the energy system. The system is EV charging station that's equipped with a rooftop solar power plant on a battery storage system, and it's connected to the utility grid. Here is the representation of that system. I said we designed a controller that command power set points of grid and the battery storage. But if it is economically beneficial or by other means necessary, we can downregulate power output from renewable generator or reduce the consumption within the limits. So the controller must optimize all of these power flows. And the whole procedure begins with making the predictions about the future states. Neural network that was trained before using historical data receives current weather forecast and outputs confidence interval with the lower and upper bounds. The desired number of scenarios is generated within a confidence interval with a Gaussian distribution. Generated scenarios enter together with state measurements the first stage MPC that solves a stochastic problem but with a relaxed model. It outputs the optimal value at risk and costs value of each scenario. And based on this information, worst alpha percent scenarios are selected. Expected value of them is calculated and passed to the second stage MPC that solves control problem but with high fidelity model, shorter sampling that ensures consumer satisfaction and provide all guarantees. Action commands are sent to particular devices that have simpler, reactive, PNID controllers responsible for actual execution of given set points. And the procedure is executed every time step with the receding horizon. So here is example of 1 day operation. Figure shows predictions that were made at midnight for the next 24 hours, and battery state is 55%. And here are the results at the end of the day, what actually happened. And thanks to prediction, battery was prepared to discharge during the morning peak before PV power plant starts to produce power. Then the battery stored excess energy and discharged later during the high electricity prices to cover consumption of EV station. An expected question is how good it is. Well, it's hard to perform tests of different strategies under the same conditions, so in the real system it's not possible, but it could be said that design controller ensures whole day of self-sustainable operation. And it's not just about the 1 day, but the presented controller is embedded into the energy management system of given microgrid to perform continuous real-time operation based on minimizing costs, maximizing overall benefits of the whole system, and non-stop for several months already. And with this, I conclude the presentation.